Okay, welcome back, everyone. So this is the time for questioning discrete world. Well, we open the floor for all the questions you can ask to Jerji and Sumati. Jerji is online and Sumati is here, so the floor is open.
Last question. Why is root quantum gravity discrete? Sorry.
Is it a question? Okay. I was. Do you, Sumati? Do you have something to continue with for the Richard's question?
No, but I did ask, there was the question by Yanda, I think it was for Jackson. What is the question?
No, it wasn't just.
Okay.
Yeah.
So I'm still a little bit puzzled about this insistence of causal sets to be a finite pose set. So I've probably asked that question like 10 times and I'm still trying to understand it. So what is really the advantage of insisting so much on a finite set and that you see the continuum as an approximation? Why do you not take the continuum limit?
Okay, so a good question. So I have several answers to that. I mean, today I guess we'll also get a chance to give our prejudices in the afternoon about discrete versus continuum. But in this case, really it stems from the fact that if we're choosing a kinematic structure which is discrete, then for whatever reason, we would like to get the continuum out in the right way, right? So we know that this pose set is not enough for space-time. And if my theory is going to use this pose set or a discretized, just this pose set, it won't ever be enough for space-time. So if my causal set in this limit, without making any connection to the volume element, if I took pose sets and then they would limit in the infinite density limit to this. If I didn't worry about the continuum, this volume and number correspondence. And that you can say, I take my omega n space of all possible causal sets, and then I take limit n going to infinity, and whatever this thing that I have will contain space-time in it. But it'll only contain the space-time pose set structure. So if I want to recover volume, this is a motivation, if you like, to even start using the pose set structure as a fundamental structure, a non-metric fundamental structure. So I wouldn't know how to get back the continuum limit if I did not make a number to volume correspondence. I would not achieve what I set out to do. So I think that's the reason, one reason why discreteness in this case. So if we're using pose sets, then they should be discrete in order for me to be able to recover this in an approximate sense. But of course, there's a more sort of, you can call it philosophical, or I think of it as practical, which is that you have a finite UV finite theory because you just are summing over things. Now, so I could take this limit in multiple ways. This limit could happen if I took the density, like in a finite volume. So if I have, let's just call this a volume V, and I know that on an average, this looks like rho times V, where this is my, rho is basically 1 over the cutoff, volume, space-time volume cutoff. I can take this limit in multiple ways. I can fix the volume and then take the rho going to infinity and therefore n going to infinity limit, where I make it infinitely dense. Or I could fix a rho and take the v going to infinity limit, and I go to larger and larger space-time volume. That's the more physical limit. So it's not like we're looking at only finite n, but we're looking at finite n, which is proportional to so n becoming larger and larger, proportional to the volume at the same density. And so, if this is equal to, right, that's what you might imagine the discreteness scale looks like, right? So those two, so we don't necessarily look at finite causal sets. It's very often convenient to look at that and then take the limit. It's a question of ordering of limits. But it's not fundamental in the sense that as long as the density of sprinkling is the sort of, in the continuum approximation, you don't go to infinite density, then you're not reaching the continuum limit. So everything looks like an approximation, but you can go to infinite volume. So in fact, in the sequential growth paradigm, you actually do look at this, but it's generated through finite processes. So I don't know if that answers my prejudice, but yes.
There's a follow-up here.
Okay, yeah, that's now I got confused by trying to understand this, but I don't. Okay, so that's why I ask, I suppose. Use this volume and number correspondence, that seems to be sort of fundamental. Does that mean that you cannot do, say, conformal gravity, or would there be other ways connected to this kind of limits you were talking about that?
I think you could do, I mean,
do you have anything about that?
No, so we haven't looked at what it would look like in this framework, but essentially, but by that I suspect what you mean is that you're ignoring, you're ignoring this part and you just look at, so you don't look at this part, you only look at this. So where only the conformal factor is a degree of freedom, right?
No, actually we're thinking the opposite, that you sort of saying this conformal factor should be, shouldn't enter into your discussion.
So the conformal factor will enter. So
through this volume.
Through the number to volume correspondence.
Yeah,
so if I, for example, if I looked at two conformally related spaces, the causal structure will be the same because we know that light cones don't change under conformal transformations. But the thing that changes is the density of points everywhere, and that's your conformal factor. And that will change, yeah.
So you can't do the opposite case where the volume factor doesn't make a difference, just the conformal, not the theory, just the conformal structure.
Well, yeah, so I haven't thought about it. I mean, one might be able to tailor make something of that sort because both degrees of freedom are there. So you could just look at the poset structure and think nothing of the volume. So for example, you could, instead of, summing over omega n, you could sum over all possible omegas for all n. So n is not a fixed amount.
Right, yeah.
And then possibly, by just thinking of n as a variable as opposed to the causal structure. I mean, I don't know. I don't know the answer to it, but it's not out. Nobody has done it. Thanks. Thanks for the question. Yeah.
Yeah, it is a follow-up question to Benny. And I think I will also add one then, which is a bit of follow-up question to Jerzy. So, I mean, after you have fixed this, you can measure, I mean, for example, you have the causal Z, which gives you the Einstein-Hilbert action, which means you can measure the discreteness in terms of the Newton coupling.
Yes.
Right? Can't you now just tune this ratio or product better to 0? So discreteness length times square root of the Newton coupling. You could tune it to 0.
So, yeah, at least in causal sets, I mean, we saw that this ratio comes up in the action. So all the Newton constant, everything is sitting here. And sorry, this is straining. So what this is for us a free parameter, but you're saying make this
Just tune this ratio to
Yes.
0.
Yeah, you can. Of course you can. And that's the rho going to infinity limit. So when rho goes to infinity, that's basically what you're doing. And that's a very useful comparison to make sure that, our geometric structures that we're constructing have the right continuum limit. So we're often using limits to check to see whether we've got the right order theoretic structure.
Yeah,
But we let go of that because fundamentally, and this is where Benjamin has a question, which is basically, why do you fundamentally want discreteness? And I think my reason is very simple. I think that it makes for finite sums. It makes for a space-time volume cutoff, which is, and as you saw right now, this L is fairly well constrained in when you want, in the path integral from our arguments to be of order of the Planck scale. So, if you want
a technical reason.
Okay.
It's like saying I can better simulate on a finite lattice because I need less computing power, so I keep the lattice distance finite.
I think so. So that you can say, all right, things are finite. That's just a technical question. I don't think this is technical. If you want to make sure that certain kinds of causal sets are suppressed, taking the L going to infinity, L going to 0 limit is not going to help you with that suppression. It is helped if you have a discreteness scale which is of order the Planck scale. So you can say, well, and I think that's true of all our approaches, right? At some level, we have arguments that might seem circular because you say, well, okay, then that means the whole theory is wrong. Or you have a consistent part of your theory where you can say, if I want to suppress these things, then I have to have apply. What would have been weird is if you could only suppress it if it had been smaller than the Planck scale.
The reason I'm asking, I think it's the same reason why Benny was asking, is if you take this limit, you end up with a continuous quantum field theory of gravity. And then the question is, what is the relation? If this limit exists, and yes, there are always infinities all over the place. So let's assume you can make this limit well defined. So what are the relations to call it other theories on the market, which are defined in a continuum? So it would be...
Yeah, you can definitely take that limit. And I think that's one of the things that in Astrid's program she's trying to do. And the question is, of course, that's interesting, but and then you can compare the theories and so on. But if you want to have a finite theory, and I would say, again, the reason being that we want to be able to reproduce the continuum in a very specific sense. And that continuum doesn't exist when I take the discreteness scale to 0. That limit doesn't exist in the space of posets. Choose another way of quantizing, you're fine. But if you want to use posets...
What do you mean by does not exist?
This will be, if you don't make a number to volume correspondence, then your causal sets then the posets that you have, even if they're locally finite, will limit to things that are just the causal structure. They will not limit to the full space-time. They cannot have the information of the full space-time if you don't make this correspondence between number and volume. And I think that's key if you want to recover space-time. This is a technical point, but then you have to question the entire approach. That's all I'm saying. You may want to do that, but if you want to make a correspondence, then the limits will just be, this object here is just the conformal structure, has information only up to conformal structure, right? Only the conformal structure is contained here.
Can I? Okay.
Yeah, not the full metrical information.
Struggling a bit, but are you telling me this limit may not give us what we want, or are you telling me this limit is just going down to hell? I'm not sure.
The first, that it's not giving us what we want, but maybe it's giving other people what they want, which is fine. We're with people who do all kinds of things, and I'm happy to have posets being used in different ways. But I think the reason why one wants a continuum approximation stems from this. but also stems from various other reasons of finiteness that, we can, it's philosophical at some level also.
I'm not sure because, I mean, let's assume, of course, this will not happen in the next 30 years or even 300 or whatever. We can measure Planck scale physics. And it turns out to be continuous. What are you doing then? I mean, of course, you will not do anything
Measure that.
anymore, but I mean,
How would you even measure continuity? How would you ever measure continuity? How would you ever measure resolutions?
I certainly can measure discreteness.
Yeah, I
Okay, so I'm just asking the question, if it turns out that the discreteness scale, because we can measure there, is not the Planck scale or 10 times the Planck scale because we have measurements which have no sign of discreteness, what are you doing then? So then you would like to increase your cutoff scale. And I'm only asking, so I mean, I'm struggling a bit to understand what you really lose. You say you lose space-time structure.
So if
What does it really
so
mean?
one thing that would happen, and this is if you were able to probe scales that were much smaller than Planck scale, then my argument for removing these bad guys from the, suppressing them will go out the window. So that's a falsifiable, then the theory is bad. It's a bad theory.
In which sense?
It's a bad theory because it's the things that dominate are completely in the large N limit. We wouldn't have space-time emerging. I mean, in my
Can I
theory,
rephrase? Wouldn't we have space-time not emerging in a simple way as you have it before?
no, I'm saying assuming this framework, in this framework, it's falsifiable in this sense. That's all I'm saying. Then you should throw this theory out the window. If you could see things much below the Planck scale.
Sorry,
I have a follow-up to.
yeah, I
sorry.
mean, essentially, I will ask now the same thing to Jerzy in the sense, what do you see? I mean, for trans-Planckian scales, I mean, that I think is what distinguishes the different approaches to quantum gravity. I mean, below Planck scale, we see all the same, namely classical general relativity.
Structure.
Now it was to Jerzy. Sorry for screwing up your name.
Yeah,
I know
but
that I should know it with my Polish name, but I don't.
I don't know what to answer.
Yes.
Okay, thank you.
Just a second, Georgie. We are not hearing you. So
Oh, you cannot hear me at all?
just give us a moment. We are not hearing you. We are trying to fix it up.
But in the meantime, I have the follow-up.
Well, he already said the follow-up to Georgie, so let's wait.
Can I try saying something?
Can you say something?
Okay.
Yeah.
So in case of loop quantum gravity, we have discreteness in the sense of discrete spectra. So this is the same kind of discreteness as discreteness of harmonic oscillator or discreteness of photon. So yeah, but okay, we don't have such continuous parameter that could make this the step of this spectrum sufficiently small. So yes, the eigenvalues of some geometric quantities are quantized, and certainly Planck length is somehow characteristic, gives this characteristic scale. So, but I don't know how we could. Okay, so what exactly, in what way you would like to go beyond this scale?
Yeah.
So what you're saying is that the Planck scale is the efficient, or the Planck mass is the cutoff of your theory in a sense.
Well, I'm not sure that it's cutoff. It is just a natural parameter which is featuring in the spectra of operators. So those spectra are not necessarily, they are not equidistant like in case of harmonic oscillators. So spectrum of typically spectra of operators, they become at some point almost continuous.
Yeah.
But usually there is some lowest, I mean, usually there is allowed lowest value, which is 0. So it is not like in the case of harmonic oscillator when there is this lowest non-zero eigenvalue, but then there is a gap between the 0 and the first non-zero eigenvalue, and usually this gap is of the order of Planck lengths in suitable power, depending on the units of this geometric quantity.
So what I'm looking a bit for is something like, call it a scattering process, even though I know it's very difficult to construct this. And I mean, anyway, beyond a Planck scale, but it's also not a redeeming quality of loop quantum gravity to describe scattering. So I'm looking for a scattering process or like where I can probe trans-Planckian physics. And there I would like to understand what loop quantum gravity has to tell about it.
Okay, so tell me in what way technically you would use loop quantum gravity there, and then I can think.
I thought you tell me. I'm sorry.
I don't know what you want to do.
Well, I want to probe. Please use my phone. I want to probe trans-Planckian physics. I mean, since I'm coming from high energy physics, I think in terms of scattering processes, but everything you can give me there, which probes trans-Planckian physics, is fine with me. So you have, if you wish, free choice of weapon. I would like to understand how beyond the Planck scale, call it physics, changes or does not change. So what has loop quantum gravity to say about this?
I'm sorry, but I don't understand what specifically you want to do. And if you ask me to propose something, then I'm not sure what to propose.
Can make a small comment here, which is that even in loop quantum gravity, I think it's the fact that the area is quantized and there's
For
a minimum
example.
area. That's to me a very interesting. I mean, of course, the conclusions can be different from of that particular result, but it then suggests that at the fundamental level, it's not a continuum way of thinking about areas, right? I mean, continuum areas could just go on forever. There's a continuous spectrum. There's no reason to quantize the area. So if you're going to go back and take this information and ask what geometry is it representing, what is a kind of geometry, then it seems to me that, and Jurek, you can correct me if I'm wrong, because this is just this is sort of when these area operators came out, I thought it was very nice because it does suggest a fundamental discreteness through the mechanism of this canonical, even if it's kinematical framework. And so there is something non-continuum geometric, I don't know how else to put it, but which is emerging. And I think that basically if you are to take it seriously, then I would even go so far as to say you wouldn't see any trans-Planckian effects. There would be nothing beyond this point.
That's what I assumed, that this is really a coupler. That's why I said it. Covariant coupler, in a sense. The theory provides insight.
Okay, maybe we will move to the next follow-up question.
Yeah, I wanted to follow up regarding the question posed by Jan about taking or not the continuum limit in causal sets. And you mentioned that one aspect is that if you take the continuum limit, you cannot efficiently suppress certain configurations that you don't want in the continuum. But Isn't this question is somehow related to the dynamics? Because I mean, you have an action there, and if you would use a different Bayer action, it is possible that simply by changing the fundamental dynamics, in a sense, you can suppress these configurations, and then that would be a different way of addressing the problem where you can still take the continuum limit. And this is somehow related to another question that I wanted to ask, that is, how would you constrain the fundamental dynamics? So how would you constrain your Bayer action? Or you have infinite freedom in choosing it?
Right. So very good question. Yeah, so one could imagine that if I didn't come up with, if I didn't have the Ben-Casadauer action, I had something with, say, a different kind of, maybe the action grows like n to the n cubed or n to the 4 or some higher power of n. That kind of an action could still work because the kind of, dominance is basically giving you a dominance of n squared, 2 to the n squared upon whatever. So that may happen, but then you also would have to show that that same action could give you continuum in that limit, right? Manifold-like causal sets. And that seems, I mean, you have to be able to recover Einstein gravity, right? I mean, you have to be able to recover your Einstein-Hilbert actions. So from a fundamental perspective, it's true that that action, whatever action I pick, I can pick anything, and I can just put, instead of writing, some specific coefficients, I could, write something like, and n0 plus, I could just put in different coefficients here. And that's the kind of thing that I would like to see, how these coefficients would run. That would be an ideal, very nice calculation to do. But this particular combination that I have gives me the Einstein-Hilbert action. And if I didn't have the Einstein-Hilbert action, then I think I would be completely at a loss as to whether continuum, the classical equations would ever be satisfied. So in some regime, I may have, for example, only the first term. So for example, in the UV, maybe only this guy is there. But then these things are added on as you flow but we don't know how to do that.
Mm-hmm. Yeah, but I think the Einstein-Hilbert part of the action, you should really have it such that you recover Einstein-Hilbert, but on top of that, you can add higher derivative terms in the same manner as Astrid Gustavo did in that paper that you mentioned. And those additional terms could, if they are built in the right way, could suppress space-time that you don't want in the continuum limit, but they would be suppressed on their own because they should correspond to low curvature configuration, like as you go to the continuum limit, like to large distances. So if you think about in quantum field theory terms, or in EFT terms, as Einstein-Hilbert plus R square, R cube, all of these type of terms, those are negligible, of course, for today's gravity, but they become important at high energies. So perhaps they could act as a suppressor for space-time configurations in your case.
Yeah, that's definitely it's a very good and interesting insight into the possibility. Perhaps my worry would be that if I thought of even the standard path integral and I looked at very highly non-classical paths, even at the level of, even if you added pieces to the action, at the level that the classical action still, to leading order, they should still be suppressed by the classical action. And you can imagine that when the additional terms become relevant, become in whatever region of parameter, that's when these non-classical paths will kick in. So I think I'm not entirely sure whether we can avoid this, but it's thanks for the question. It'll be nice to have a discussion later.
Limit, I think that there are a couple of papers that I can give you.
Thanks. Yeah.
Well, I have a kind of follow-up question to both of you. Suppose if we have discrete space-time at fundamental scales, surely you can avoid singularities, which is intuitively expected. In loop quantum gravity, well, there is this loop quantum cosmology, proposals of a bouncing universe. My question to Georgi is that how robust are transition from loop quantum gravity to loop quantum cosmology? Are there any open questions which have to be understood, and what are the challenges?
Yes, so certainly loop quantum cosmology is a sort of toy model for loop quantum gravity. So so there is no exact sense in which you can derive loop quantum cosmology from loop quantum gravity. There were some works on this, and usually they show that it is not that simple as we would expect. Yes, so but it seems that this avoidance of singularity is still in some way it is always possible within full theory. So in case of loop quantum cosmology, actually this avoidance of singularity is pretty strong property. So there is even it was shown that the quantum operator of energy density. So we have quantum operator of energy density. So this is energy of some dust or some matter which collapses together with the universe. That this quantum operator is bounded from above, and it is bounded by some critical value, which is just a fixed number for all the models. So it's not a property of a state; it's a property of operator. So every state has to obey this inequality, because this is a strong property of operator rather than of some states. So we are not sure whether the same continues to be true in the full theory.
Okay. I have a similar question to Sumati. I have not heard of any kind of non-singular cosmology coming from causal sets. Maybe if you can tell something about this.
Yes, this is a part of the talk that I didn't, the third approach where we look at a growth dynamics of causal sets, where you basically you construct a labeled growth element by element, which is either related, has elements in the past, or is unrelated to the elements. So it's in a broad sense a causal growth model. And you can, so that's this framework in which these things appear, but you can definitely think of these objects, which are bounce-like solutions. And I'll just sort of briefly give a sense of what they're like. But you can have multiple bounces like this. And here we're looking at the class of past finite posets. So which start off with, so they're finite to their past. So in this class, if you look at posets, then you can define in a very covariant way what is this object here, which is we call a post, which means that everything is either to its future or to its future or to its past. And you can have multiple posts of this sort, at various times. And they're completely non-singular from the discrete perspective. There's nothing happens there. But they're not also described by any continuum geometry. So they're resolved in a sense without recourse to a continuum geometry. There's no equivalent continuum structure that is here. What's nice about these posts is that you can show in this dynamics you have I mean, there's actually a very nice way to do renormalization here, which is that you start off with a bunch of coupling constants in that dynamics, and then it goes through a post, and it's like a forgetting. And then it goes through another one, and then it forgets, and then it goes through another one. And you can see that you can construct a renormalization group flow, which is a cosmological renormalization group flow, whenever you have such forgetting times. And the coupling constants then in a class of models, those are classical models, have fixed points, which actually correspond to the simplest dynamics you can construct. So this cosmological renorm, this is a very nice, so we think of it in multiple ways, but to actually flesh out realistic models of this sort are, at least at the moment, beyond us. So we have models which exhibit this property, and you can actually force such things to happen at, in a stochastic way. And then they renormalize your theory. There's some nice ways to think about it, but that's as far as I can tell. There's no real cosmology that we know how to construct from it. Something that looks like Friedman, Robertson, Walker. Yeah.
Any further question?
So this is a question to Surya, and it's on a completely different subject. To me, one of the most interesting things about quantum gravity is the fact that derivative interactions, this is in the continuum version of the theory, that derivative interactions push you slightly outside the light cone, so that there is some very, very small probability for superluminal propagation. Or to say it another way, it's the metric field operator that controls what the light cone is, and it's a fluctuating variable, as all things are in quantum gravity, or in quantum field theory in general. And there's some probability, very small, but some probability that something could sort of surf the outward fluctuations of the light cone and propagate much more rapidly than the sort of average light cone. It seems to me like your formalism here entirely precludes that, because it's based on just enforcing causality in a hardwired sense. But perhaps I'm not seeing something. Can you comment on that?
Good question, because I think this sometimes when we say order, so one thing that I want to say, order is like a proto-causality, okay? So it's a structure on your set. So we should also realize that when I'm talking about things that are far from the continuum, that order doesn't translate into light cones in the way we think of it, right? So there are fluctuations of things which are non-light cone-like in the deep quantum regime. But in a sense, this is something that, so if you are dealing with Lorentzian spacetimes and you're calculating these things, you're talking about the same class of structures that we are, because a Lorentzian spacetime comes with a causal structure attached to it. But when you fluctuate, you go from one Lorentzian spacetime to a neighboring one, and you're looking at that, and one imagines it to be a light cone widening or not, but it's a matter of, if we knew how to interpret that quantum theory well, then it's simply the fact that you have, superposition of two distinct causal structures. That's going to happen here as well. It's not hardwired into the, when I sum over all possible causal structures, whatever physics that I'm doing will be a superposition of causal structures. So in that sense, light cones do fluctuate. All of that is in here. So there's nothing hardwired into the dynamics. It's just a discretization where you're identifying from your Lorentzian geometry a substructure which is sort of at the heart of the spacetime. But you're going to have summations over causal structures for sure. Or in your case, integrals over causal structure. That is the source of your fluctuating light cones, because you're actually looking at possibilities of, you start off with some metric and you've got a perturbation. That perturbation could either shrink or expand your light cones, And so you will have related effectively it'll look like your light cones are widening. So here too, I mean, so here in the very deep ultraviolet, we have a sort of, I shouldn't say very deep ultraviolet, but in the small, even in a continuum-like causal set, we have things where the light cones don't look quite like they are. They're doing the opposite. They're shrinking to something very effectively look like they're shrinking, because on the scales of the discreteness scales, things are further apart than they appear. So we have interesting emergent properties, but fundamentally what you have is a superposition of causal structures. And I think that's, in that sense, it's the same as in the continuum.
So, would you say that your theories allow for violations of microcausality?
Insofar as any Lorentzian theory would, I think it would be perfectly fine. Insofar as a Lorentzian theory will have a fluctuation, which can be interpreted in this theory as an effective. So, I mean, I think it depends very much on what we mean by violation. If we mean that there are superpositions of causal structure, then for sure, with respect to one causal structure, it'll look like a violation. But if you're going to say, okay, well, effectively there's another causal structure, then it looks like it's moving out of the light cones. That kind of thing can happen, but it's only to the extent that it can happen for strictly Lorentzian spacetimes. If you're going to let go of the Lorentzian character of a spacetime, a causal character, then this will not be, then there will be a divergence. But yeah, so if you are going to look at a theory of Lorentzian causal spacetimes, then those effects should have a version, a finite version in these theories. I don't know how, but yeah, they should have, in principle.
Is there a scale associated with this? It's a Planck scale. Can I have different scales?
Yeah, so I do have like in my, when I write down the action, I have this discreteness scale, which I don't put equal to the Planck scale because I want to have that freedom. And you can construct effective, you can construct discreteness at different scales. You can look at coarse grainings at different scales, and that sort of thing should show up in your theory, show up in the characteristics of those theories. So yeah, that's in principle a free parameter.
There is non-locality. Whenever we have
which this non-locality, so it's in a given causal structure, you have non-local features. So you're not violating causality for that one given causal structure, but what you do not have is the ability to completely localize, although you can construct quasi-local structures like the D'Alembert operator for a scalar field, or a scalar curvature, which is quasi-local. You can construct that. But this particular feature that I was showing earlier, which is that you have for every E, you have, nearest neighbors that go all the way up the light cone. And they're all equally, why is one nearest neighbor better than another? And if you have infinite number of them, then you have to distribute your love equally to all of them. And then you have nothing left to give anyone, right? So it's really in that spirit that you've basically got, in a Lorentzian structure like this, nearest neighbors in the strictly Lorentzian sense, not in the Riemannian sense, but of course it's finite. In the strictly Lorentzian sense, gives you a graph which is infinite valency, for example, in Minkowski spacetime. And then you have to deal with that non-locality. So every physical thing that you want to construct in which has the right continuum kind of structure should have at least quasi-locality. And that's what one tries to do in this. So you recover some kind of quasi-local structure, but the theory itself in the deep quant UV would have all of these things contributing equally.
No? Okay, then I will take the opportunity to ask last Benjamin.
Yes, sorry to come back to this, but I was just thinking this relation between number and volume. If you don't have that, do you just describe unimodular gravity then, or how should I think about it?
Unimodular gravity would be where you fix the volume. So in fact, unimodular gravity is where omega n is fixed. That would be the right way I think of it.
Okay.
But if you don't have the number to volume correspondence, I think these are the kinds of theories that maybe Lee has worked with some other people. And there's just a theory of posets. And then I think there's nothing constraining you. So we're very constrained by continuum considerations, even in the construction of our dynamics, even in the construction of any of the geometric invariants that we have, are constrained by the continuum. That constraint cannot come if I don't have a number to volume correspondence. So otherwise, it's just a theory of graphs, and I can just do anything. And I'm not saying that other people are just doing anything, but for us, the continuum approximation, that's why it's the second line of my hypothesis, that you have to have that number to volume correspondence. If you don't have it, then it's not causal set theory.
Thank you.
So is there an analog of 3 volumes in this setup? By volume, you probably mean the 4 volume, which we did in the conformal factor. But is 3 volume of any importance here?
Can you hear me? Yeah. So it is actually, there's a very nice construction. It has to be induced. First of all, if you think about a point process of a Poisson point process, then it's, lower dimensional objects are a set of measure 0. They can never appear. They cannot appear explicitly. Nevertheless, you can reconstruct something. So, Cauchy hypersurfaces are out for this reason, but you can reconstruct things that look like that. And there's a very nice way to actually construct the total volume, the spatial volume. So if I have a causal set which has, so I'm just going to write it like a continuum because it's easier to put the dots in. So let's say that this is my anti-chain, which is like a final boundary for my causal set. Then it is a very nice way to reconstruct so if I look at all the elements, so this is a final set, it's a future-most set, and then I look at all of them to the past, which are just links, okay, which have volume 0 or volume 1, if you want to count this, up to the surface. This according to the volumes. And actually, that's a very nice way of even doing a covariant time evolution in the continuum. You can just take space-time volumes and then use it as a time parameterization. But in any case, if you take the set of elements like this and the set of elements like that, and you and I can't remember the formula, but there's if you just count this and you take the difference, you recover the volume of the surface. So you can construct the volume of the n-1 dimensional surface. And what's more, you can also construct the Gibbons-Hawking-York term by taking different combinations of this. So we have a very nice construction. I can't, remember the coefficients. They're not easy. But the point being that you're basically using, so if I think of an anti-chain as a bunch of points which have no information, so spatially related points in this theory have no information. They're just dust. All the information that you get, and I really, I have the thought experiment is simply that anything we measure is a causal measurement, okay? So nothing we can measure in real life there's no spatial measurements we can actually do. They're all induced by causal things that we do causally. So if I have something like this, then I can, I can induce structure onto this by looking at the neighborhood. And there's ways of constructing a distance function between points, and just by looking at the volumes of this past element, here the future element up to this point. So if you look at that structure, you can construct the spatial homology groups from this. You can construct, and this is an interesting homological construction, and you can also construct a distance function, and now we're actually trying to see if we can construct something similar to the kind of quantum Ricci curvature that people study in CDTs. We have a version of that which we are trying to study now, but just using the induced information. So you need the space-time to induce information onto the spatial hypersurface. And if you then thicken this enough, then you will reproduce the equivalent of your Cauchy hypersurface. Yeah.
Thanks.
Okay. Still tempted to ask very short questions, Sumati, if it is okay. So you started with the Minkowski space-time causal structure. Is there any way to understand from this building block to arrive at de Sitter space-time?
So Minkowski spacetime is just an example, because you can do a point process, as I think Faye was saying. You can ask a graduate student to throw points on any spacetime and construct the causal set from it. So any causal spacetime has an underlying poset structure, and you're just discretizing that poset structure. So, so de Sitter for sure, we've studied de Sitter. We've studied it quite extensively in terms of both looking at it geometrically from the point of view of the causal set. People have studied that, but also for studying how quantum fields live on this. So scalar field theory on de Sitter space and constructing the scalar field vacuum. And I think that, so that's definitely something that we can do.
Okay.
Yeah.
Thank you. If there are no questions, let's conclude this discussion. Then let's thank Georgi and Sumati. And